a great pleasure to welcome the last speaker of the first session of the afternoon, which is Dr. Juncai He, who is a Bing postdoc at Austin right now. And he is, again, an expert in computational mathematics and in particular deep learning and stochastic optimization.
Yeah. So hello, everyone. So first, thanks a lot for the nice introduction from Professor Jabin. And also thanks for Professor Xu and Professor Harnim to run this workshop. Today, I'm going to talk about how to involve and how to apply the mathematical structure to study and to understand both real deep neural networks and also for the convolutional neural networks. So this is joint work with my a PhD advisor, Professor Juncai He, and also some other collaborators like Lin Zhang, Yuan Chen, and Chunyue Zheng from Penn State and Peking University. So let's start my talk about a brief outline. So basically, I have two topics, right? How to involve multigrid in real DNN and how to involve multigrid in CNN. So first, I will talk about this connections between real deep neural networks and the linear finite element method. I will finish this section by identifying that these two things are just the same thing. Yeah, and then we will try to see how to involve multigrid in real deep neural networks. So basically, this the key point is actually to study the hierarchical basis approximation for some very special function, like x squared or multiplication functions. Then we will see how this composition structure will come out naturally. Then we move to how to think about how to involve multigrid into CNN. So first we will talk about some basic structure of CNNs, and this I guess the most popular structure is ResNet, and we will try to use this constraint linear model to interpret what's the rule of this basic block in this ResNet, and based on that one, we will further try to study how this multigrid, how can we use multigrid to study CNN. Especially, we will see that, okay, actually, we can obtain this new type of CNN that is called MgNet by just modifying a typical geometric multigrid with with only a minor modification. Then I will try to finish with some concluding remarks. So first, let's for simplification, let's start with some notation first. Okay. So first, this is like this function, this deep neural network functions are function of class. Okay, so this is from RD to R. Okay, and then this is so-called hyperparameters like N1 to NL. Some in computer science or machine learning, we call it as like the number of hidden the number of hidden neurons at each layer, and we can also say just like the dimension of this. Linear mappings during each linear transformation. So here, okay, this is a simple version of this DNN. So it's like a recursion. So we do here in this notation, we do activation first, and we do linear mapping later. And this is like actually affine mapping something, yeah, right? Because we have this so-called bias term. So here, because we based on this previous recursion, we do activation first. So initially we need a linear layer here. So here, basically this is like a linear activation, linear activation, linear activation, then finish with a linear. So here for all this presentation, we will just focus on ReLU activation function. If we say sigma without special notice, we just take this sigma as ReLU by default, okay? So this ReLU is, I guess, one of the, not one, just the most popular activation function in both, I guess, machine learning and scientific computing if we apply deep learning techniques. So here, this is a simple notation, like to say if we have like the constant width the deep neural networks. So if this n1 to nl just equal to the constant n, we will just to denote this as n dn for some okay. Then the first thing is about, of course, approximation property for DNN is among the most attractive topics during for DNNs. The first thing is like to say, okay, how this just one hidden layer? Okay, so before we go deeper, we just think about what's the approximation property for one hidden layer. So basically, so this is like it's a beautiful result. I guess just to be proved like last week or sometime, yeah. This is like if we define this, okay, this is so-called the spectral barren norm, like you extend a function to a global function, because this function is originally defined just on a support compact set on in this RD. So here, this f hat is like the Fourier transform of this function. Then this theorem tells us, okay, this is only for a one hidden layer. If you have n neuron, this is for ReNu, and for just L2, this is a special case. Okay, you have an upper bound that is n to the -2 times a log n. So there's no dimensionality, you can say, right? In some sense, this overcomes this the so-called curse of dimensionality. And then the later thing is, in some sense, also very beautiful. It's like we can also have the lower bound, right? And more if you involve like a ReNu K as activation function, then you can obtain some approximation or some error estimate for sublevel norms. Then this allows you to like to apply this to like PDE as to numerically solving the PDEs. So okay, I assume that Jonathan will talk about this beautiful results during his talk. I guess tomorrow evening. Yeah. So okay, right? We see that the DN1, just one hidden neural networks, has such a amazing, actually, in some sense, approximation result. So why we still want to go deeper? So why do we need a deeper NN? So maybe is this some expressive power, like this kind, just to do representation or more, or this is just like a approximation power. We can achieve something. We can achieve some faster approximation. So to start this one, let's just go do some example to explain why is these steps really helps to do something like to do representation or to do approximation. So first one is like, okay, if we only focus on 1D, so 1D is simple in some sense. So for this 1D case, this is like a hard function, like this is like the beautiful basis function, right? For 1D finite element function space. So here, this is a simple connection. We can just use 3 neurons, just one hidden layer, 3 neurons to recover this basis function, this hard function exactly. So this means that, okay, just for 1D, a linear finite element is totally contained in this DN1. But the following question is that how about 2D? What if we move to 2D, things becomes totally different. One of the main feature we can see from the next diagram, that is, if we still like here, if we have 2D and we have like 50 neurons, we will see that this mesh, the grid created by this deep neural networks, the mesh is just created by some string lines globally. There's no line segment. There's no local line segment. It's just a global some string line globally. Also, if you have a higher dimension, then you will have some just some hyperplanes to cut your space to have some mesh. So, but here for general for typical adaptive grid, you will use some line segments and to create some local triangles and to have this kind of beautiful mesh. So this theorem tells us if you have a higher dimension, which is greater than 2, this basically this DN1 cannot cover this kind of function. Basically, this proof is just based on if you investigate can this DN1 can reproduce the basis function for this 2D finite element method, because we know that if you can recover basis function, then you can recover the general function, right? Because by compilation, then you can just to make a wider DN, and then you can do the representation. Okay, so this is the first example. If you do not do some deeper neural network, you cannot achieve some representation power. So the next thing just tell us actually, if you really go deeper, you can really recover every piecewise linear function, like a linear finite element you want. So here is a result. Like okay, if you have some certain mesh and for this finite element, then you have n degree of freedoms, then you can have a DNL. You can have a upper bound for both the depth and the width of this neural network. So here is KH is like the largest number of because each basis function you have a support set, right? For this support set, there are some element. So for each basis function, you can find some the number of the element in each support set. So you choose the largest one. And okay, if we have some regular, like if we have a regular mesh, we can have some upper bound for this KH in something, right? But here, the good thing is that you have a log. You have a log of KH. So this is like, okay, like this here for this example, for this DN2. But here, for this example, for DN2, we can just have some, really, we can have some local, right? Local line segment. So this that we can hope we can hope that we can create some mesh like this by just adjust the weights of the parameters, right? So then basically we just finish this topic that is linear finite element method just equal to the real deep neural networks. Yeah, again, basically this is what Professor Xu mentioned during this opening remarks, right, about his first point. Yeah, very thanks for this referring. So this so by here we still want to say, can this multigrid structure be involved to study why a deep neural networks is needed? So here is his idea. We just focus on this specific theorem. This I assume that this one is in some sense recently this one is very popular. I get after there are like more than hundreds of papers just follow this result to have a bunch of new approximation result for DN for especially for real deep neural networks. But okay, originally this theorem tells us, okay, if you have a special function which is just x squared on this interval 0 to 1, then you can have a DNN. This DNN you have a constant width. That is a constant like 7. But actually, if you want to do something special, like if you can reduce the width, but that's okay. Okay, if you only focus on the depth, then you can achieve approximation result like this. Sorry, okay, this is a typo. This should be -2 times this L plus 1 together. Okay. So anyway, so here this is the structure of this F tilde, the neural network. This is a linear one, right? Of course, for ReNU you can reproduce linear easily. But here, this GI, what's a GI? The first of the G1 is we discussed it before, because this is a 1D program. Okay, this G1 is like the hard function, and you can use 3 right neuron to recover it. Then this GI, that's perfect. This GI you just compose this G1 I times. Of course, because by the definition of deep neural networks, it just means that you can recover this GI by using a D layers DNN, right? Of course, you fix the length, but there is only 3. Here, okay. The following question is like, how to understand this kind of beautiful result? Is this result just a coincidence, or is there some intrinsic mathematical principle to guide to or to understand this one, or have some other interpretation? The other one is, can we extend this kind of super convergence property for more general or specific functions, right? Like if you have some polynomials, trig functions, you can still have some structure like this, and then like you have a global basis like a G1, G2, and this then you can find some composition structure among this G1, G2, G3. Then you can say, okay, you can use a deep neural network to recover this function efficiently. Then the last question is like, can we apply this for more general case? Well, we can achieve x squared. What else we can obtain from this result? So let's answer the three questions one by one. So the first one is like how to understand the structure, the construction of this f tilde of this this beautiful result for the x squared. The idea is just you think about hierarchical approximation for x squared. Hierarchical, okay. Originally, hierarchical basis methods like to allow as a foundation for this sparse grid, right? But here we just we forget about the sparse grid first. We just focus on the so-called hierarchical basis approximation. Okay, for this very special function x squared. Okay, here we think about we have a uniform grid. Okay, with size which is HL equal to 2 to the negative L. Then we have this kind of basis function on each level, right? This is for the 0, 0 with 0. This means that okay, you need to fix right the two endpoints like the boundary conditions, and then this V1 you have the first hard function, and then this V2 because here this V1 V2 is like the entire finite element space for the with the uniform grid, right? So okay, let's say if we define this IK as a uniform interpolation for this function, okay, keep in mind this f is x squared, okay, this f is x squared. So this phi k is like the i's basis function of this on case level, or you can just say this like the basis function associated with this xki, right? So here, this is like the hierarchical decomposition, or right? I guess like in some other papers, we have some fancy way to introduce this hierarchical decomposition. But here, this is just like a technical sum for this original IA interpolation. Okay, so here we will say that what is I0F? I0 it just means that you think about these two endpoints. Then this interpolation result for this exponential function x squared is just a linear function x. Then the amazing part is that what's this ik minus 1 for this f for the x squared? The answer is that okay, this phi k 2j minus 1 just is this is the standard hierarchical basis that to say you just choose this old basis function with the old order. Okay, then you will see that the key observation is that the coefficient for this basis function, they are equal. It's just a constant that is independent with I or with j. That just depends on this level k. Then we found that okay, this gk we discussed before by we used to define the DNN. This gk is just equal. It's just exactly equal to this compilation, like this just a compilation of the hierarchical basis function on each level. So here is a diagram. Okay, so the key observation is that if you have a function fx that is equal to x squared, this simple function, okay, then this function will you can approximate use this f tilde. That is a DNN, okay, with this structure. But in the same time, from different direction, what's this f tilde? This f tilde just exactly equal to the uniform interpolation for this a square function on a uniform mesh. This is like the graph of this G1, G2, G3 G4. So based on this key observation, we can have some new and essential interpretation for this DNN structure, right? Of this, why this F tilde should look like this, because that is just simple. That's just, in some sense, that's just like you rewrite this uniform interpolation by using this this kind of hierarchical approximation. And the key idea is that you will find that this GI defined by the summation of this basis function of hierarchical basis function on each level. This GI has a very special composition structure. Okay, of course, if you know, okay, this F tilde is actually equal to this interpolation, right? From the perspective of finite element, you can apply this result to say, okay, then you can have like a H1 error estimate, W10 error estimate, or you can make sense like this, right? You can apply this. You can apply all that you know for this uniform interpolation on this on finite element to this to obtain some extra property for this F tilde for this DNN, right? Okay, so we finished the first question. We found that okay, this F tilde is not a coincidence. This one is just like a rewrite, just reform the uniform interpolation with this hierarchical structure, with a hierarchical basis approximation structure. So this is the first. So this here we involve right multigrid structure to study this DNN. So okay, now let's follow the second question. Can we like to extend this for some other functions, such that we can have some other spatial polynomials or trig functions? We can construct something like this, right? If we can have some UX, this UX can be written as this GK is with the same definition. So here, if we can do this, is GK has the same definition. We can say, okay, here because here if you choose any decay for this mu k, this sequence will converge to some function in H1. Okay, so then you will say, okay, then you can represent or you can approximate this UX by using DNN again very efficiently. So, but here we prove that if you got some regularity, right? Because here you can just you can just make a cutoff. You can say, okay, this mu k will equal to 0 if k is greater than some positive number. Then you will say a piecewise linear function, right? Then that piecewise linear function you can use this real DNN to approximate efficiently. But here, not approximate, just represent. Okay. So, but here, if you give some regularity for this function, if you assume this function have some extra smoothness, you will say, okay, there's only quadratic function, nothing else. So from here, if you have some real smooth function, there's only square x to a square, only the square function that you can achieve such an amazing approximation property. So then we move to the third question. Can we like this, if we have x squared, if we can recover x squared efficiently, then what else we can do? Can we like to say some more general function, or can we do some high dimensional cases? So here, this is an example. This is the idea. If you have x squared, actually you have multiplication, right? So if you have multiplication, you have polynomials, then you can do everything like multidimensionality. This is the example. Think about if you have fx that is x squared, then you move to the x phi x that is xy. Then this xy can be, this is a very simple, just a simple algebraic identity, right? This is algebraic identity. Then for this algebraic identity, you use the x squared. So if you repeat the x squared by using a DNN, this f tilde, then you construct a new DNN FL, this phi L, okay. Phi L is a DNN. This can be used to approximate this x times y multiplication function. Then you will say, okay, you can involve any express grade method, like a spectral method, and other kind of like also high order finite element method. you can involve all this kind of classical result to obtain some new approximation result. For example, here, if we involve this Taylor explanation or like spectral method, we will say that, okay, for this quite smooth U, we can approximate this U efficiently to achieve a convergence, exponential type of convergence. Okay, but here this result is very similar to the Professor Yi's result, but here we do not need to string the domain. We can just have the entire domain. Okay. The next one is that how about the long-smooth function for 1D? Because for long-smooth function for 1D, we know that for like Babushka and Professor Schwab, they have this beautiful HEP adaptive finite element method. So we can approximate this U by n degree of freedom with exponential convergence. So here we have this ReLU. We can also obtain a similar result like this. Okay, I guess this Wednesday, Professor Schwab will talk about more details about this kind of exponential convergence rate by using ReLU DNN, also for, I guess, for different kind of functions. So how to understand? Okay, follow the question. How to understand this phi-L? This phi-L is not just like a tensor product of this, because we have this following result. This is not like, because this one, okay, this phi-L, again, this phi-L is what? Is a uniform interpolation for linear finite element. If you think about it, this is just like a simple tensor product, then this means that you should have like a bilinear interpolation in some sense, right? But here you just have a pure linear finite element interpretation. So this is an example. If we think about it, right? Originally, we think of hierarchical for this interpolation. We know that is go back to the DNN. But here we know this DNN equal to interpolation first. So we go something in a different direction. We think about what's this? Can we have some composition structure for this hierarchical FEM? So here, the beautiful thing is that if you have this just on this pi1 minus pi0, you got here this base function, right? Here, this is a base function associated with this mesh for this 2D finite element. But here, this function, okay, this function only works on this domain 0, this cubic 0, 1 cubic. If you go outside, then this function is not equal to 0. So, but thanks for this property of the ReLU, we can cut off for the function outside. So here we got something like this. This is like a formula here, right? This ReLU2. This ReLU2 is G2. This G2 is a piecewise linear function 1D. So you can use one hidden layer. This ReLU1. This is a typical one. ReLU x minus ReLU x minus 1. This is you can use two hidden layers. So here this function is two hidden layer deep neural networks, and this will equal to the basis function globally, which means that for the outside of the cube, this function will equal to 0. And then this function you will only have a locally supported set. So based on this one, we can have the following theorem to say that, okay, for any like uniform mesh, okay, of course you can like to have a linear transformation for this uniform mesh, and then you can just to write down this representation of this function explicitly and concisely. So here, this is a remark. Like originally, we have the result that right, this finite element on 2D cannot be reproduced by this white hidden layer. And also we know that if we go deeper, but in our original result, we prove that like for this case, we need at least 4 layers to represent this function. And this Aurora has a result is to say that, okay, actually you can just have 2. Actually, you can just have 2 to represent this function explicitly, but there is almost impossible to write down this to write down the explicit formula concisely. That is pretty complicated for this one. Okay, so I guess I just finish this part like to say how this multigrid can be involved in DNN, especially for this second part, like how to understand this newly developed the approximation result by just think about hierarchical approximation for some special functions. Okay, Then we try to move to say something about CNN, how to actually originally to involve multigrid into CNN in some sense is more naturally I guess, because first thing is like to say there are many ideas to try to understand CNN. First one is like a approximation property, like right, which is very similar to a DNA case. But recently, this dynamical system view to understand this ResNet is very popular. We have many works on. There are many works here. But here, if like here we recall two very classical examples like LeNet and AlexNet. So what's the key feature of this kind of function CNNs? In my opinion, the two main features, like especially for like image classification program, what's the key features for this CNNs? Of course, one is like you have a convolution operation, right? You have a convolution with multi-channel, then you need a multi-resolution. You should do like downsampling or you say pooling, and then you of course if for just the image classification, that's enough, right? But anyway, two things: one is convolution, one is multi-resolution. Okay, so here, but sometimes how to do this convolution structure becomes can give you different architecture of your CNN. For example, here you have this ResNet. I guess computer science guys like this kind of diagram, but here we try to write down by using formulas. Okay, here like this for this basic block, it's like you input R and you do convolution and you do activation, you do convolution again, and then you add the bike, but then you add this activation later. But just after this ResNet paper, this pre-active ResNet, this is proposed by the same authors with this ResNet, okay, just by Kai Min He, these guys. And they found that, okay, if you move this sigma here, if you move the activation function here, then you will achieve a better result, like especially you can do deeper. So this is a mathematical description for this like a pre-active ResNet, right? For each like each layer we say, or each different resolution, we have this kind of basic block first. This is like an iteration, right? You do activation, convolution, activation, convolution, add together, and then you go to next block. And here, if you meet with a pooling, this pooling is okay. There's some, I guess this is some kind of computer science trick to like to save some extra layers. But here, okay, that's okay. Like some different efficient way to involve both this pooling and this smoothing together. Okay, so here the key program is like what is the pre-active ResNet, the basic block doing, like this block? What's this? This is like a iterative scheme, right? What's this block is doing? So we hope to understand this basic block from this simple model, this constrained linear model. Like, okay, originally, actually, you just want to solve this E is called the feature, right? You want to use the feature to do image classification. This is actually, originally, this is just a pure linear system, but you have this nonlinear constraint, okay? So namely, you want to recover this phi. So, but you have some question, right? What is this A? How to solve this equation, right? So our idea is that just apply multigrid, try multigrid for this one. Then before we try multigrid, the first thing is like, okay, of course, multigrid is we have two parts, right? Smoothers and also pooling, like restriction and prolongation, right? So, okay, we first think about this smoother, that is a residual correction scheme. This is like, okay, you have a first guess of the solution, you form the residual, you do this, you solve the residual, okay, and then you update. So this is a basic iterative method, right? So this is some example, okay. Then you specifically, if this is like you do iteration for U, okay, like for the feature we mentioned before. But if you do if you look at the iterative scheme for this residual form, just for the residual part, you obtain result like this, right? So let's think about Okay, that is for linear. But now, okay, for saying we cannot avoid this kind of, we cannot ignore this nonlinear, right? So here, how to involve nonlinear? The idea is like, okay, think about, this is like a, right, residual correction scheme. The first is, because this B is like the Jacobi. If this A is like a 5-point stencil, and then this B, you will see that if you apply Jacobi, you will see that this B is also a convolution. Okay, if you apply Jacobi twice, this is you just have different kernel. Okay, so this is like you without a nonlinear constraint. But here, think about our original constraint that is positive, right? Like you solve Navier-Stokes equation, you need this. You have some physical constraint for this pressure, right? So you need some positive scheme. So here, the simplest way to have this kind of positive constraints, like we just drop the negative values, right? So we have this this kind of. But here, the amazing thing is that even we involve this nonlinear activation function, we can still have this following iterative scheme for the residual. That's a key point. That's a key point because the appropriate position for this activation function is okay. So you can still have this residual. So let's think about if we have a nonlinear iterative scheme like feature extraction like for the equation 25, then we will say that okay, this R, we will how about the iterative scheme for this R? We will say this 27, right? This R scheme. Let's have a comparison with this pre-active ResNet, right? We say that there's only differences that here the AL, this second kernel, will independent with this layers. That will only depend on this level, like the resolution. So here, this is a very simple modified pre-active ResNet, right? So this is like a diagram to show, okay, if you more familiar with coding this one, okay, for basic block, you have convolution first and convolution later. So you just each the resolution, you just share this A. So these are some. So if we believe this interpretation are true, are real, works to explain this kind of ResNet, we have some numerical experience here. Like this one is for CFR10, right? Consistently, we will have less parameters and higher accuracy, also for CFR100. Okay. So based on this one, we're trying to say how to because right, the previous one is like we just focus on like the smoother part, right? Like on just one level. If we involve multi-level, we have a multi-grid scheme, right? Here, this is we just rewrite. Okay, we rewrite this multi-grid scheme. We recall this for linear case. Here, this is like a pre-smoothing, right? Then we do prolongation. Here, this trick is like we involve a nonlinear, like the full approximation scheme, but we still have a linear case. Okay, so we have this kind of interpolation, and here we will have the like a GL plus one. GL plus one is like a really approximate for this a right term, not a residual, right? Because originally multigrid is like you do cost level for residual and cost for residual, but here we have a approximate for the right term on cost level. Okay, of course, if for general like V cycle or slash cycle, we have like a prolongation and post smoothing. Okay, let's say then it's good time to propose this MgNet, right? We just add one. This is really a minor modification. We just put two activation function. Of course, okay, here we need a theta to increase the channel. Okay, but here this is really like just a very simple modification. So every time if you have code this multi-grid before, then you just find your code and to add some activation function, you got MgNet. This is like okay, typically for computer science, for communication, they will like to have like a diagram. But here actually, I guess this preserved code is simpler. for communication with guys who have this background for multigrid and finite element. So here is just some thoughts about this MgNet. The first one is, okay, what is multigrid? Multigrid is like you have this system, right? This AL is like the operator for system, and the BL is like the smoother, and this PIL, RL like the restriction and prolongation. They are all given a priori, right? If you have PDE, you discredit, and then you give everything a priori. But for what's CNN? Okay, so first, as we say before, CNN has almost the same structure as multigrid. You have smoother. Multigrid still have smoother, because if you have like a 5-point extension, then this system A is smoother. As we mentioned before, right? This B smoother can also be a extension. And actually, we proved that in our paper. This pi, for some finite element method, this restriction and this prolongation are also some convolution with stride 2 or some deconvolution with stride 2 with certain kernel. So okay, of course, then you need to train these operators, and also you need a nonlinear activation. That's we call it minor modification. And one other thing is that we are still trying to understand is what's the rule of channel. Okay, basically here there are some notes and papers containing all some technical results about these connections of this MgNet and the CNN. We can say that typically we can prove that they are really just very, very close to each other. So here we show some, okay, I guess I still have some few minutes to show some numerical experiments to identify this MgNet really works. Okay, so first one is like, okay, we make some comparison, right, with some popular classical CNNs. The first one is like, okay, think about it. We have CFR 10 is MgNet, right? You can say here it is 2, okay. If you have ever do some coding for this, if you have ever done some coding for this AlexNet, you will be very familiar with this. What is 2. Basically, this 2 in multigrid is like for on each level you will do the smoother twice. Okay, so that's 2. But for AlexNet 18 is 2 means that on each level you will have like 2 basic blocks. So they are extremely the same thing. Okay, this number is like the channel. So here, this is like a comparison on this CFR 100. We can still say that we have less parameters but higher accuracy, right? This is on MgNet. Okay, if we try this like this model, we have this, and also here this BLI means that on each layer on each block we will do not share this B. Yeah. So this is like okay, like this is some comparison, right, to show the power of MgNet. Here we would like to explore the features of MgNet itself. Like we want to see the stability and the scalability for MgNet. Actually, this is very important now, right? Because when we propose like the AlexNet or DenseNet, people will say, well, you have AlexNet 18, you have AlexNet 34, and you also have like AlexNet 102, something like this, right? That means that you need your structure to be very consistent. You can extend your structure to achieve a better result. Here we can say, okay, both on CFR 10 and 100, right? We can show some consistent numerical result. This is for MgNet. If we increase the depth, like okay, it's like just increase the number of smoothers on each level for multigrid, then and also sometimes you increase the channels, make a wider MgNet, then you achieve this numerical result. So hopefully I can finish this in 1 minute. Okay, so this conclusion is like okay, if we involve for multigrid and the DNN, we found that if we involve hierarchical basis idea, we will have some new very interesting mathematical features to understand why the depth is useful for DNN. And the other one is okay, we will just say that the MgNet, that is just saying both also multigrid. Multigrid saying there's only just a minor modification. Okay, some future works I just have a very quick comment, like okay, for example, approximation from the viewpoint of a finite element, and also especially like both finite element and the multigrid are most of the two powerful rules in numerical PDEs. So can we apply this kind of techniques to solve PDEs? And also we know we have a geometric multigrid. Of course, we will think that we can apply algebraic multigrid. Algebraic multigrid, you will have like a graph. So can we like have some algebraic multigrid to have some graph salience? So I guess I just conclude my talk here. So thank you for everyone's attention. Yeah, welcome to for questions.
Thank you.
Thanks.
Just on time. So we have time for questions. Let's give people.
So I have one question for the last point you mentioned for the graph network. So sure. Here you basically your CNN is the regular mesh, the standard mesh, structured mesh. Then you can use multigrid. But if we consider graph network, which if we compare with the finite element, basically it means unstructured mesh. Then do you think, or can we directly apply what you told here to graph network, or do the similar way?
Very good point. Very good question, actually. Yeah, I guess we can do that. Yeah, of course, because basically we have two, right? One is if you have a long regular mesh, like for finite element, you have some crazy mesh, and you think about this as kind of like some abstract graph, right? Then we can construct some also. Professor Xu has many works about this multigrid for unstructured mesh, something like this. Then we can also try to involve this kind of techniques to study how to construct graphical CNNs. This is the one. If we know this like the fine mesh, the unstructured fine mesh a priori, if we know. But sometimes like for some social neural network, right? For some social network also just social network, right? You just have some point and you have some edge. This means that in some sense you just have an abstract graph. This actually is very close to this algebraic multigrid. Algebraic multigrid means that we just give you one matrix. We just give you one matrix. Based on this one matrix, you can say, okay, each node, right, and corresponds to each like a row of this matrix. And if this there's a non-zero enter of this matrix, then you can say, okay, these two node will have an edge. Then you can construct a multigrid method to solve that kind of matrix. Okay, but so for this viewpoint, if you really meet with like a social network, so I guess we can use this idea from algebraic method to begin with some abstract graph to construct some graphical CNNs. That's I guess that's a potential project. Yeah, thanks for this comment.
Okay, thank you. Thank you for the comment.
Thank you. I don't yet see questions in the chat or the Q&A, but let me ask one. Sure. It seems to me that from this you can get a relatively good understanding, not only good performance, right, but a good understanding of which neural net you should pick. What should be the dimensions, for example? Am I correct?
You mean for DNN case?
Yeah.
Good point. You mean this tells us of, okay, if we know, like if we want to employ DNN to solve some PDE, right?
Yeah.
And then we know some like a priori information about the solution of the PDE. Like is this one is a smooth function or just a function with some singularity?
And then can you use that as an insight in how to build because that's always a bit of an issue, right? That you always have to play around with the dimensions of the net.
Sure. Yes. Good point. Just like this, right? If we know, okay, this function is a smooth function, we can maybe choose this U-har here based on this construction, or okay, but this result is tell us, okay, we can have or just a consistent or uniform structure to do approximation. But sometimes we can adjust this kind of a structure to have a higher approximation rates. Right? Yeah, so if we know some information about the target function a priori, this will tell us something, right? Like to how to build a more efficient neural network. Yeah.
All right. We have a general question in the Q&A. Why should I use DNN FEM instead of classical finite element method? Efficiency?
Good question. You mean to solve PDE, to solve PDE, or to do something else, right?
I imagine to solve PDE, right?
Okay.
Finite element.
Good question. I guess one solution is like this. For Professor Shui's result, like this here. If you solve high dimensional PDE, the first thing is like you will meet with the curse of dimensionality with the classical method, right? If you have a classical finite element to solve a PDE on just 100 dimensionality, something like this. But how to construct the mesh, how to construct the matrix, and how to solve it. But here, you just need to construct one hidden layer deep neural networks, and you will achieve a quite amazing approximation result that is independent of with this dimensionality. So this is like the first thing I can say. I guess there are much of other reason why there's a huge potential for using DNN in solving PDEs, like especially for the first talk from Professor George Kantakis mentioned, right, to involve this in physical systems.
Yeah, but in general, you would say, right, that the main motivation is computational time.
Right. Yeah.
You expect those methods to be a lot faster than the equivalent pure.
Yeah. Yes, that's the first thing come into my mind. I guess that much because I have lots thought about this direction too much.
But do you have any example? For example, I mean. Did you do, for example, the finite element, the pure finite element calculation, and can you compare it with just to give an idea of the gain of how much faster?
Yeah, basically we have
the
one
neural
actually.
net method is
for 1D we have one. Like we have initial we use adaptive finite element to approximate the function, and then we based on that one we set up about the same number of the neurons. Like then we train the DNN. We will find that okay, we can really have a better adaptive mesh based on DNN. We can really have a better approximation adaptive mesh, such that result will lead to lower energy for that solution for DNN. But sorry, I guess I should show that. I should include that one in this slide.
Thank you. Any?
Yeah, maybe maybe add some comments in.
Sure.
Response to that question. Why should I use the finite element instead of classical FEM? That's a hard question to answer. Many people have advocated the use of DNN for numerical PDEs, and at this point, for me, my personally is mainly a personal theoretical interest, and like the what Juncai pointed out, which I think Jonathan will talk tomorrow. If you consider the finite element as piecewise polynomial, and for ReLU is piecewise polynomial, linear of degree first degree. The approximation probably is for some crazy reason, which you can actually prove is so much better. And so potentially there's many people will argue that because of that, especially this, all the multi-dimension results is like a one-dimensional result. But in that case, you may think that's probably less, less because of dimensionality when high dimensional. For the low dimensional, we can also argue that in some cases, like it's easier to construct conforming piecewise polynomials or stuff like that. But at the end of the day, if you're talking about efficiency, you have to solve this optimization problem. So far, we just, it's a matter of research, and it's still a topic of research. It's just, there's no efficient method to solve this minimization problems. If you use stochastic gradient descent or any other kind of things, you can achieve certain accuracy, but it's difficult to get the asymptotic rate you theoretically can prove. So in the low dimensional case, I would not use it right now. For a high dimensional case, there's a region I do not personally have numerical experiences for high dimensions. Certainly there's potential there. And a theoretical question is that why the same piecewise polynomials, one gives you so much better approximation property than the other. That's a quite a remarkable property of a neural network. And but somehow it's very closely related. As a functional set, they are the same set if you're talking about piecewise linear functions. But there are different structures to produce this set. And so you really have the same kind of function class, but it's a different linear algebra, different way of solving it. So it provides lots of things for somebody like me doing finite element for ages. So think about from the different point of view why this piecewise polynomial given by the neural network has such a remarkable properties. Anyway, sorry, this is kind of a long answer to a simple question, but it's a very interesting theoretical topic to investigate. Many people have a lot of hope this is going to do well, especially for high dimension. And we're going to see how it's going to evolve down the road.
Okay, thank you.
Yeah, thanks for the comments.
Yeah, I don't see any other questions. And it's almost 5, so I believe that we can conclude this session by thanking again all our speakers, and we will reconvene at 7. Thank you all.